Now we're going to get into what this section is really about, approximating area. Our goal in this endeavor is to say, okay, suppose I have any crazy shape that I like, I can find the area of that. Okay, now I know how to find the area of things like circles and squares and rectangles. And if I have a shape that has a bunch of straight sides, you can often break it up into things like triangles that fill up all the space. And then you can use your knowledge of trigonometry and geometry to find the area of the whole object by adding up triangles. But if I have something that has rounded edges like this, I can't fill it up with known shapes. So I'm not going to be able to build off my existing area formulas. We need to find something new or find a technique that will help us here. In math, however, we don't like to start with the hard problems. We like to start with the easy ones and then build off of that. So we're not going to start by finding the area of just some random shape. We're going to start by finding the area of something easier to work with, but we'll be able to expand into something like this later. So here's my simplified version. Let's suppose that I have some function, y equals f of x, and I have a starting and an ending point, a to b. What we're going to do is we're going to look at the area under the graph of this function from a to b. And the reason that we're going to do this is because this has three straight sides. The only curvy side we have is on the top. That's going to make things easier to work with. But because my top portion is bounded by a function, any function I like, that gives me the flexibility to look at weird shapes. And that's what we're going to be able to use to build off of in the future. So in the future, we could say, well, if I know how to do this with a function on top, then maybe I can use a function on bottom, and we can add functions on the sides, and we can get to whatever crazy shape we want. So now our goal is going to be find the area under a function from x equals a to x equals b. All right, well, I picked a simplified problem, but we still have the same issue. If I have just some crazy shape and I don't have any geometric formula to build off of, then how do I find the area? What we're going to do is we're going to start with an approximation. We're going to draw in a very simple shape inside that will approximate the area. And the simple shape that I want to use is a rectangle, because rectangles are nice and simple. So here's what this is going to look like. Suppose I have my function, a to b. What I'm going to do is say, let's break our interval a to b up into pieces. Maybe I'll break it up into 4 pieces. And on each piece, I'm going to draw a rectangle. Now, I need to pick a height for the rectangle, and I'm just going to decide to pick, I'll go up until the right-hand side of the rectangle hits the function, right, hits the graph. So that gives me some rectangles. You can see, even by my crude graph, that this doesn't exactly give us the area. It gives us an approximation. We're going to approximate the area under f of x with rectangles. One of the key pieces that we're going to need for this to be effective going forward is all of these rectangles are going to be the same width. Okay, so what I want to do is outline this process with an example. So let's suppose I want to approximate the area under f of x equals x squared from 0 to 2 using 4 rectangles. We'll just make a little drawing to help us along the way, but we don't really need the drawing in order to do a problem like this. So here's my x squared function. And I want to go from 0 to 2. We're going to break this up into 4 rectangles. Okay, and I can see that based on the way I've drawn this, it looks like my rectangles are going to be an overestimate. Okay, but let's go ahead and see if we can write out what this is going to look like now. So the area is approximately the area of these 4 rectangles. So I can say the sum from 1 to 4. I'll just say rectangle sub I. Okay. Each rectangle has width. They're all the same. If I'm going from 0 to 2, then I have this distance of 2 that I'm breaking up into 4 pieces. So it's going to be 2 over 4. The way that I got this is I'm looking at the interval that we're taking the area under, right? In this case from 0 to 2. By subtracting, I can find out how far that is, right? So you can think of this as 2 minus 0, divided by how many rectangles I'm breaking it up into. Okay. As a general formula going forward, what we can do is we can say, I'm going to call this width delta x, and the formula for it is b minus a over n. So there's our general formula for the width of a rectangle, delta x. We will use that again in the future. Okay, the next thing we need to do is figure out how tall each rectangle is, and in order to find that, we need to figure out where these endpoints are. Because where that rectangle ends, that determines the height by plugging that into the function. What we want to do is say, all right, I'm starting at 0, and for the first rectangle, I'm moving over by 1 width. Width we have is 2/4 or 1/2. So for the first rectangle, I'm going to start at 0 and move over by 1/2 to get that first endpoint. For the second rectangle, I move over by another 1/2. So it's like starting at 0 and moving over by 2 widths of a rectangle. For the third one, I move over by 3 widths. And for the last rectangle, that should be at the very edge of my endpoint, or moving over by 4 widths. As a general formula, if I want to get the right-hand endpoint for the ith rectangle, that xi is going to be a plus I times delta x. Start at a, and I move over a number of widths equal to whatever rectangle I'm looking at. So this is another formula that we're going to want to reference later. So to get the height of my rectangles, I'm going to take these endpoints and plug them into the function. In this case, our function is x squared. My area is approximately the sum of these 4 rectangles, which is going to be the width 1/2 times the height. First one is the height of 1/2 squared. Second one is a width of 1/2 and a height of 1 squared. Third one is a width of 1/2 and a height of 3/2 squared. And the last one is a width of 1/2 and a height of 2 squared. In the future, because that width is the same each time, we'll probably just end up factoring it out. So when I compute that out on my calculator, I get 3.75. We'll just write it as a decimal. Okay, I want to try this problem again. We'll go through another example. This example, I used the right-hand endpoint, the right side of the rectangle, to determine the height of the rectangle. I didn't have to do that. Let's look at this same example, except using the left side of the rectangle to determine the height. Once again, I think it might be helpful to have a drawing here just to keep track of what's going on. So the difference between this problem and the last one is that now it's the left-hand side that determines the height of the rectangle. So if I look at my drawing here, I can see that my approximation will be an underestimate. Okay, so let's go ahead and compute that out. The area is going to be approximately the sum from 1 to 4. I'm adding up 4 rectangles. Each rectangle has a width of delta x and a height of f of xi. We've already computed the delta x, and we've computed a bunch of xi's. The difference here, if I'm going to use left endpoints, is that for the first rectangle, I don't want x1 the way that I defined it before. I want to use the x0. So for left-hand endpoints, instead of starting from 1 to 4, I want to roll everything back by 1. So we'll go from 0 to 3. Okay. So from before, delta x is b minus a over n. So that's 2 minus 0 over 4, or 1/2. The xi's I've already have written out. The only one that I need to add in is that x0 is 0. Okay, so now I can say, all right, this is going to be 1/2, factoring that 1/2 out, times f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. Those are my 4 endpoints, left endpoints. My function is squared, and when I compute this out, I get 1.75. So I know that the actual area is going to be somewhere between 3.75 and 1.75. This example, we were using left endpoints. In this example up here, we used right endpoints. Going forward, we're going to stick with just right endpoints for our examples. We could have other options too. We could also pick the midpoint and use that to determine the height of each rectangle. And there are advantages to using different techniques. In the next section, though, what we're going to do is we're going to find an exact area using infinitely many rectangles. So a left and right or midpoint won't really matter. The difference between a left endpoint, a right endpoint, a midpoint, or instead of using a rectangle, maybe using a trapezoid or something like that, those techniques matter when I don't want to use infinitely many rectangles to find an exact area. That matters more when I'm finding an approximate area numerically. So we'll save that discussion for another day in Calculus 2. Okay, so let's go back and discuss some terminology here. The sum from I equals 1 to n of f of xi delta x is called a Riemann sum. When we stick to right-hand endpoints, I can write it out this way. So this is a Riemann sum, right endpoints. If I write out the sum from 0 to n minus 1, f of xi delta x, another way to write that would be to say, well, all I'm doing is I'm picking a different type of endpoint. So instead of taking the exact same endpoints, x, 1, 2, 3, 4, 5, and so on, and rolling them all back by 1, I could also relabel my xi's. I could use a different symbol for that. So I could instead say, all right, go from 1 to n, but don't use xi, use something else to label these as left endpoints. So we could maybe label this as something else. I'm going to put a little star on it. In this case, xi star is any point in the ith rectangle. So if we use this, we're not talking about a left-hand endpoint or a right endpoint or a midpoint. We could be all over the place. This is a more general way of writing a Riemann sum, and let me explain why this is going to be helpful. In order to find the exact area, what I want to do is start by saying, all right, if I have my interval from A to B, and I use 4 rectangles, we'll just stick with right-hand endpoints for now. So here we see if we divide our area into 4 rectangles, we can approximate the area. But if I divide into more rectangles, then I get a better approximation of the area. So the more rectangles we use, the better. So if I want an exact area, the answer is to use infinitely many rectangles. Now, the problem that we run into is if I had infinitely many rectangles, I couldn't draw them. And if I knew the area for infinitely many rectangles, I could not add that all up. So we get around that. We do a very sneaky way to get around infinitely many rectangles. We're going to look at computing the area of finitely many rectangles, and that area is a number. And I can think of finding the area as being like the output of a process, like a function. So I'm going to take a limit as that area function goes to infinity. So the exact area under f of x from x equals a to x equals b is given by, I'm going to take this same Riemann sum from 1 to n of f of xi star, which for our purposes we'll just use right-hand endpoints and it'll be xi times delta x. And what I'm going to do is I'm going to throw a limit in front as n goes to infinity. So I'm doing that same process of finding the area of rectangles to compute to give me an approximation, and we're just going to take a limit as that number of rectangles that we use for our approximation goes to infinity.